next speaker is Margherita Lelli Chiesa, and she will talk on the conjecture of Donagi-Morrison.
So, first of all, I would like to thank the organizers for the opportunity of being here and giving a seminar. So, today we'll talk about a conjecture of Donagi and Morrison, which concerns the Brill-Noether theory of curves lying on K3 surfaces. So, I will start by recalling some Brill-Noether theory. For us, C will always denote a smooth irreducible curve of genus G over the complex field. And having fixed two integers R and E, the Brill-Noether variety WRD of C parameterizes a line bundle of degree D on C, having a space of global sections of dimension at least R plus 1. This is an honest algebraic variety whose expected dimension outside of W R plus 1 D of C is given by the difference G minus R plus 1 times G minus D plus R. This number is generally denoted by rho d GRD and is known as the Brill-Noether number. We call a line bundle A, which lies in WRD of C, but not in WR plus 1. That means that over there we have equality. A complete GRD on C. I need to recall another definition. So we say that a line bundle A on C contributes to the Clifford index if both H0 of A and H1 of A are at least 2. And in this case, we define the Clifford index of A to be the difference, the degree of A minus twice H0 of A plus 2. The Clifford index of the curve C is by definition the minimum among the Clifford index of A, where A runs over all the line bundle contributing to the Clifford index. So, from now on, we will concentrate on the situation where C lies on a smooth projective K3 surface S. We denote by L the corresponding line bundle on S, and we assume L to be ample. In this situation, if S and C are general enough, C behaves well from a point of view of Brill-Noether theory. This was proved by Lazarsfeld in 1986. His theorem states the following. Assume that the Picard group of S is cyclic generated by L, and this hypothesis is satisfied by a general K3 surface. And let's see a smooth curve in the linear system defined by L. Now, if the Brill-Noether number is negative, then the variety WRD of C is empty, as expected. While if the Brill-Noether number is non-negative, and moreover C is general in the linear system, then the variety WRD of C is smooth of the expected dimension. Now, an important remark is that since for any genus G we can find a pair SC satisfying the hypothesis of the theorem, this implies that the same statement is true for a general curve in the moduli space MG. And this is a classical result, the so-called Giesecke-Petri theorem. Now, a natural question is what happens if S and L are arbitrary, so without the hypothesis on the Picard group of the surface? We will concentrate on the cases where the Brill-Noether number is negative. Unfortunately, without the hypothesis on the Picard group of the surface, Lazarsfeld theorem fails, as one can see in the following examples. So, let S be a 2-to-1 cover of the projective plane branched along a smooth sextic. We denote by H the pullback of the hyperplane section, and we consider a curve C in the linear system defined by 3H. Now, such a curve can be of two different types. It is either a 2-to-1 cover of an elliptic curve, in which case one can show that it has a G14 coming from the G12 on the elliptic curve. Or it is isomorphic to a smooth plane sextic. In the second case, we have no G14, but we have a G15. However, both for k equal 4 and 5, the Brill-Noether number rho 10 1k is negative. So C does not satisfy Lazarsfeld theorem. Another example is given by considering S a general quartic hypersurface in P3. We denote by H the hyperplane section, and we consider a curve C in the linear system defined by 2H. Then C has genus 9, and it is the complete intersection of S with a quadric Q. And one can easily see that a ruling of Q gives a G14 on C. And the corresponding Brill-Noether number is again negative. Now, in both these examples, the K3 surface has Picard group which is cyclic, but the existence of a GRD having a negative Brill-Noether number comes from the fact that we are considering C not in the linear system which generates the Picard group, but in a multiple of it. Analogous phenomena occur when the Picard group of the surface is non-cyclic. For instance, if S is a quartic hypersurface in P3 containing a single line E, then its Picard group is generated by the hyperplane section and by the line, and here there are the intersection numbers. And the curve C in the linear system defined by 2H plus C has a genus 6, and the restriction to C of the hyperplane section gives a G25. Again, the Brill-Noether number is negative. Now, this last example is important because in this example, the GRD having a negative Brill-Noether numbers is given by the restriction of a line bundle which lives on the surface. The Donagi-Morrison conjecture predicts that something similar always occurs. In order to state the conjecture, I need the following definition. We say that a line bundle M on S is adapted to L whenever both M and the L tensor M dual have a space of global sections of dimension at least 2, and the Clifford index of the restriction to C of the line bundle M does not depend on the choice of the curve in its linear system. Now, I remark that the first condition assures that the restriction to C of M really contributes to the Clifford index, while the second condition is satisfied if either H1 of M vanishes or H1 of L tensor M dual vanishes. The Donagi-Morrison conjecture states the following. Let A be a complete base for point free GRD on C, and assume that the degree is at most G-1 and the Brill-Noether number is negative. Then there exists a line bundle M adapted to L such that the following are satisfied. First of all, the linear system A is contained in the linear system obtained by restricting M to the curve C. In other words, A dual tensor M tensor rho C is effective. And secondly, the Clifford index of this restriction is at most equal to the Clifford index of A. So the first condition is equivalent to requiring that for some divisors A in the linear A0 in A and M0 in M, and note that A0 is a divisor on the curve while M0 is a divisor on the surface, A0 is contained in the intersection of M0 with C. So we expect that GRD with a negative Brill-Noether number are contained in other linear series which are cut out by divisors living on the surface. Now, oh, sorry. Oh, yes. For instance, in the first example we have talked about, one can show that both the G14, if C is a 2-to-1 cover of an elliptic curve, or the G15, if C is a smooth plane sextic, is contained in the restriction to C of the pullback of the hyperplane section. This is a G26, and one can show that the inequality on the Clifford indexes predicted by the conjecture is satisfied. Again, in the second example, one can show that the G14 on C is contained in the restriction to C of the hyperplane section. This gives a G38, and in these cases, the Clifford indexes of the G14 and the G38 are equal. Now, the conjecture is strictly connected with some vector bundles on the surface, the so-called Lassas-Fermukai bundles. I recall the definition. So if A is a complete base point-free GRD on a curve C lying on a K3, then A can be seen as a globally generated sheaf on the surface. So this evaluation map is surjective, and the Lassas-Fermukai bundle ECA is by definition the dual of the evaluation map. By dualizing this short exact sequence, we find that ECA sits in this other short exact sequence. So in particular, H0 of A dual defines a subspace of the space of global section of the Lassas-Fermukai bundle of dimension equal to its rank. One can easily check that the Lassas-Fermukai bundle E associated with the pair CA satisfies the following properties. First of all, it is globally generated outside of the base locus of omega C tensor A dual. And we will often assume that omega C tensor A dual is base point free, so E is globally generated. Then the Chern classes of E only depend on the pair C and A. Indeed, its rank is R+1, its determinant is L, and its Chern class equals the degree of A. Then both H1 of E and H1 and H2 of E vanish. And very important, the Eulero characteristic of E tensor E dual equals twice 1 minus the Brill-Noether number. This last property is quite important because it implies that when the Brill-Noether number is negative, the Lassas-Fermukai bundle cannot be simple. That is, it has some non-trivial endomorphism. So, how to use these bundles in order to approach the conjecture? So, let E be the Lassas-Fermukai bundle associated with the pair CA, and assume that we have proven the existence of a line bundle N on S, which is adapted to L. So we have this diagram where the horizontal row is given by the definition of the Lassas-Fermukai bundle, and gamma and N is an injection of N inside of the Lassas-Fermukai bundle. Now, since N has a space of global sections of dimension at least 2, we do not have any homomorphism from N to OS. So the composition alpha composed with gamma gives a non-zero element of the space of global sections of N dual tensor omega C tensor A dual. But by adjunction, this is also equal to the space of global section of A dual tensor the determinant of V over N restricted to C. So the line bundle M, whose existence is predicted by the conjecture, we have a good candidate for this line bundle M, that is the determinant of V over N. And the problem of proving the conjecture reduces to finding such a line bundle n. Now, what is known about the conjecture? Donagi and Morrison soon proved the conjecture for R equals 1. Their idea was the following. If E is the Lassas-Fermukai bundle associated with a pair CA where A is a G1D with a negative Brill-Noether number, then E is a non-simple bundle of rank 2. We can assume it not to be decomposable because the decomposable case is easier. Then, by a theorem of Atiyah, there exists an endomorphism phi of E which is nilpotent. And E is given by an extension of this form, where N and M are line bundles on S, and XE is the ideal of a zero-dimensional subscheme XE on S. So N is the kernel of phi, and tensor XE is the image of phi. And so the line bundle M, whose existence is predicted by the conjecture, is the line bundle M appearing on the right. And in order to prove that it is adapted to L and that the inequality on the Clifford indexes wanted by the conjecture is satisfied, one uses that since phi is nilpotent, there exists an homomorphism from the image of phi to the kernel. I have proved the conjecture in the case R equal 2, which involves the study of Lassas-Fermukai bundles of rank 3. The main idea was to bring into play the fact that that if E is non-simple, then it cannot be mu-S stable, where the mu-S stability is the slope stability with respect to L. So we can replace the use of the short exam sequence used by Donagi and Morrison in the case R equal 1 by with short exam sequences coming from considering the Harder-Narasimhan or the Jordan-Holder filtration of E. The key point in the proof is the following. Let A be a G2D on C such that the Brill-Noether number is negative, and we denote by E the corresponding Lassas-Fermukai bundle, which is non-simple of rank 3. Then the Harder-Narasimhan filtration or the Jordan-Holder filtration of E has the form 0 and E, where N is a line bundle on S and the quotient E over N is a mu-L stable of rank 2. Now, this fact is absolutely non-trivial, since a priori there might occur other type of filtrations. For instance, the maximal destabilizing sheaf of E might have rank 2. But it turns out that all the other types of filtrations are not compatible with the inequality rho dg2d less than 0. So we have found that E lies in such a short excess sequence where N is a line bundle, and in order to yes, the candidate for the line bundle M appearing in the statement of the conjecture is the determinant of E over N. And in order to show that this is adapted to L and that the inequality on the Clifford index is satisfied, one uses the Bogomolov inequality for E over N, this inequality on the slopes coming from the fact that N is destabilizes E, and some other facts. But in any case, one really makes use of the fact that this short exam sequence is the maximal destabilizing sequence of E. The problem of extending this proof for arbitrary R is that when R increases, also the rank of the Lassas-Fermukai bundle becomes higher. So there are a lot of types of filtrations that might occur, and it's not possible to control all of them by hand. So in the last part of the talk, I will talk about some approaches in order to prove the conjecture, or at least to study it for arbitrary error. This is still a work in progress. So a possible strategy is to use coherent systems, that is pairs EV, where E is a coherent sheaf on the surface and V is a subspace of its global sections. There is a notion of stability for coherent systems, depending on the choice of a polynomial Q with rational coefficients and positive leading coefficients. And we will fix Q to be equal to the Hilbert polynomial of S. With this choice, a coherent system EV, where E is a two-dimensional sheaf on S, turns out to be semi-stable if E is torsion-free, and for any subsheaf F of E, having defined V prime as the intersection of V with the space of global sections of F, the following inequality is satisfied. That is, the dimension of V prime over the rank of V or over the rank of F is at most equal to the dimension of V over the rank of V. And if equality holds, one compares the reduced Hilbert polynomials of E and F. A first very good news is that with this choice, if a pair EV is semi-stable, the evaluation map from V tensor OS to E is generically surjective. A second good news is that if the Brill-Noether number is negative, the coherent system consisting of the Lassas-Fermukai bundle endowed with all of its global sections is not stable. So we can look at its maximal destabilizing sequence, which has this form, where E1 is a vector bundle which is generically generated by its global sections, and E2 has no torsion and is globally generated by the sections in the subspace V2. Now one can show that the one-dimensional locus where E1 is not generated by global sections is a possibly empty union of -2 curves. And for simplicity, from now on, we will assume that S contains no -2 curves, no elliptic curves, and no hyperelliptic curves. However, this hypothesis is not really necessary. So, in particular, under this assumption, E1 is globally generated of a finite set. So, E1 and E2 are a particular type of sheaves that we will call generalized Lassas-Fermukai bundles. So, for us, a generalized Lassas-Fermukai bundle is a torsion-free sheaf E on S, such that H2 of E vanishes, and either E is locally free and generated by global sections of a finite set, or E is globally generated, but we do not require it to be a vector bundle. So, a first remark is that if both condition 1 and condition 2 are satisfied, and H1 of E vanishes, then E is a classical Lassas-Fermukai bundle associated with a pair CA, where C is a smooth curve lying on S, and A is a line bundle on C, such that both A and omega C tensor A dual are base point free. In general, what we have is that if E is a generalized Lassas-Fermukai bundle, and we take a general subspace lambda of its global sections of dimension equals to the rank of E, then the evaluation map from lambda tensor OS to E is injective, and the co-kernel is a pure sheaf of dimension 1 on S that we call B, which is supported on an integral but possibly singular curve x. So B is an element of the compactified Jacobian of x. So this second remark motivates the definition of a generalized Lassas-Fermukai bundle, something similar to what we have for a Lassas-Fermukai bundle occurs. Given a generalized Lassas-Fermukai bundle E, we define its Clifford index to be equal to its second Chern class minus twice the rank of E minus 1. And in the case where E is the classical Lassas-Fermukai bundle associated with a pair CA, the Clifford index of E coincides with the Clifford index of the line bundle A. One can show that, the Clifford index of a generalized Lassas-Fermukai bundle is non-negative, and that equality holds only in the following cases. That is, either when E is a line bundle, or when E is the Lassas-Fermukai bundle associated with a pair C omega C, with C being a smooth curve. This proposition comes directly from Clifford's theorem for Lassas-Fermukai bundles, but it requires some more work for generalized Lassas-Fermukai bundles. And our remark is that both the shifts C1 and D2 appearing in the maximal destabilizing sequence of the coherent system ECA H0 VCA are generalized Lassas-Fermukai bundles. Now, coherent systems and generalized Lassas-Fermukai bundles enable me to prove some results. The first one is a complete description of the linear series computing the Clifford index of a curve C on a K3. Indeed, if A is a GRD on C, lying on S, such that the degree is at most G minus 1, the Brill-Noether number is negative, and the A computes the Clifford index of the curve, then A is of one of the following types. It is either equal to the restriction to C of a line bundle living on S, and this line bundle M is adapted to L, or it is a G1D, in which case one can show that there exists an embedding of the surface S in some projective space, Pn, such that A is cut out by an n-2 plane, which is 2n-2 second to the curve C. So in particular, the conjecture holds for all the linear series which compute the Clifford index of a curve. And the idea of the proof is to use the fact that being a generalized that since E1 is a generalized Lassas-Fermukai bundle, its determinant contributes to the Clifford index, and one has the following equality. So if the Clifford index of A is minimum, the same holds for the Clifford index of the determinant of E1 restricted to C. That implies that both the Clifford index of E1 and of E2 are 0, so one can use the previous proposition. And in particular, this theorem provides a new proof of the fact that the Clifford index of smooth curves in the same linear system L is constant. This is a classical result due to Green and Lazarsfeld. The use of coherent systems also brings into light a relation, the fact that the Donagi-Morrison conjecture is strictly related with the existence of some second varieties. So I recall that if there is a line bundle inside of W at 0 C, and we fix and we fix two integers f and d satisfying that inequality, the variety of second divisors v, e, e minus f of a parameterizes divisors E of degree small e on C, such that A minus C has a space of global sections of dimension at least R plus 1 minus C plus F. This is again an honest algebraic variety whose expected dimension is given by this difference. And we call this variety the variety of second divisors, since in the case where A is very ample, this variety parameterizes E minus F minus 1 planes, which are E second to C embedded in pair. We say that the pair CA has some unexpected second varieties up to the formation if it can be deformed to another pair C prime A prime, such that C prime lies in the same linear system of C, and A prime is again a GRD. And moreover, there exist two integers R and D, such that this second variety to A prime is non-empty, but its expected dimension is less than 0. I managed to prove that if A is a GRD on a curve C lying on a K3, such that the Brill-Noether number is negative, and if we assume that the pair CA has no unexpected second varieties up to the formation, then the Donagi-Morrison conjecture holds for A. And the idea is to show that, to consider the maximal destabilizing sequence of the coherent system ECA H0 of CA, and to show that as soon as the rank of E1 is greater than 1, one can create some unexpected secant varieties on some deformation of the curve C. So in this way, the Donagi-Morrison conjecture becomes a question of secant varieties, and actually the existence of some unexpected secant varieties on the curve C might even cause the failure of the conjecture. But until now, no such example is known. So, thank you.
We have time for a quick question, I think. Well, if there are no quick questions, can we thank the speaker again and we resume at 11:30 after coffee.